Here's a picture that looks a lot like a real architecture. A database for your main data, a document store off to the side, a search service, a vector database for the new AI features, and a queue. 5 separate things, and every one of them is something that you run, watch, and pay for. For a lot of these, you don't need a separate box at all. One database can do the job of the document store, the search engine, the vector database, and the queue without you ever leaving the database that you were already running. That database is Postgres. This is not a new, trendy thing. Postgres started as a research project at Berkeley in the 1980s. And in the big developer surveys, year after year, it's both the database the most people use and the one the most people say they want to keep using. So here's the plan for the next few minutes. Section by section, Postgres absorbs one more tool you thought you needed on its own. And I'll be straight about where it shouldn't. First, something you already know. Postgres is a relational SQL database. Tables, rows, joins, the SQL you've been writing for years. The interesting part is that Postgres was built to be extended. There's a real defined way to plug new data types, new kinds of index, even whole new abilities into the core engine. Some of what we're about to see is built in, some of it you switch on with one line, create extension, and the engine grows a new skill. So when someone tells you Postgres is basically MySQL with a different logo, that's what they're missing. It's less a database and more a platform that keeps growing with the tools you'd otherwise stand up beside it. Let's go through them. Start with the document database when you'd typically reach for Mongo to do. Postgres has a type called JSONB. You store a whole JSON document right in a column, then you query inside it. Give me the email of every user on the Pro plan, and you put an index on the JSON so that query is fast. Schema-less documents when you want them, sitting in the same database as your strict relational tables. No second server to run. Next, search. And I don't mean like %word%. I mean real text search. Postgres breaks a document into searchable words, matches your query against them, and ranks the hits by relevance. It handles stemming too, so running matches run. For a great many apps, that is the search box, finished, without standing up Elasticsearch next door and keeping 2 copies in sync forever. Now the one everybody is asking about. AI features want a vector database. You store embeddings and find the ones nearest to a query, for semantic search and for RAG. That's the pgvector extension. Switch it on, keep your embeddings in a column, and ask for the 5 closest. Your whole vector database is now one column in the table that already holds the rest of the row. And location. The PostGIS extension turns Postgres into one of the most capable geospatial engines anywhere. Distances, shapes, regions, the 5 nearest stores to where I'm standing. People build entire mapping products on it. And quickly, because the list keeps going. Listen and notify, give you publish subscribe. Select for update skip locked, turns an ordinary table into a safe work queue that many workers can pull from at once. Partitioning handles tables big enough to be their own time series store. And foreign data wrappers let one Postgres reach into another database and query its tables as if they were local.
Add that up. A document store, a search engine, a vector database, a maps engine, and a queue. None of which you deployed, none of which you monitored. One database, one backup, one set of credentials. That's the whole pitch, and we're not even halfway in. Before we go under the hood, a quick detour. SQL that most people only half use. Window functions first. Say you want a running total, every row plus everything before it. No loop in your application, no clever self-join. You write sum of amount over order by day, and each row carries the total up to that point. Rankings, moving averages, every customer's third order, all that. Common table expressions, with. Let you name a step and build a query in readable stages, instead of nesting it 5 levels deep. And a recursive one walks a tree in a single query, an org chart, a category tree, a thread of replies, all the way down. 2 more. Insert on conflict do update. Inserts the row, or if it already exists, updates it in one statement with no race between the two.
And returning gives you back the row you just changed, the new ID or the updated value, so you don't insert and then turn around and select it again. Small things. Together, they delete a surprising amount of application code. Now, suppose your query is slow. Why? Put the words explain, analyze in front of the query, and Postgres runs it and shows you exactly what it did step by step, with real timings. The usual culprit is a sequential scan, Postgres reading every row in the table to find a handful. The fix is usually an index, a lookup structure that jumps straight to the rows you want. Add the right one, run explain again, and watch the same query fall from reading the whole table to an instant jump. And there's more than one kind of index. B-tree is the default for equality in ranges. GIN is the one that makes JSONB and full text search fast. That's what was doing the work earlier. GIST handles geometry. BRIN is for enormous tables that are already roughly in order, like an append-only log of events. Match the index to the job. But an index is a trade. It makes reads faster and writes slower because every insert now has to update the index too. So you add them where reads actually hurt, not everywhere. The rule is simple. An index buys read speed with work done at write time. Thousands of people are reading and writing the same rows at the same instant. In a lot of databases, that means waiting. A writer locks a row, and the readers queue up behind it. In Postgres, a reader never waits for a writer, and a writer never waits for a reader. How? Postgres doesn't change a row in place. When you update, it writes a new version of the row and leaves the old one sitting there. A transaction that started a moment earlier keeps reading the old version, the consistent snapshot of the database it began with, while the new version is being written next to it. Everyone sees a coherent picture as of the moment they started. That's how reads and writes slide past each other without colliding. It's called MVCC, multi-version concurrency control, and it sits at the center of how the engine works. But if every update leaves an old version behind and a delete only marks a row dead rather than removing it, doesn't the database just grow forever? It would. So Postgres runs a cleanup called vacuum that reclaims those dead versions and an auto vacuum that does it for you in the background. This is why I never tune Postgres eventually catches up with people. The cleanup is doing real work you can't see right up into the day it can't keep up.
So how does Postgres make sure a crash doesn't lose or scramble your data? It writes down what it's about to do before it does it. Every change goes into a write-ahead log, the wall, and that log is safely on disk before the change ever touches the real data files. The rule is just log it first, then apply it. If the power dies in the middle of a write, Postgres replays the log on restart and comes back consistent. That's the D in ACID, durability, and Postgres takes the whole set seriously. And that same log does a second job for free. Stream it to another server, and you've got a live replica. Let's talk scale. Read side scale is easy. That same wall stream feeds read replicas, and you spread your reads across them. Writing is the hard part. One primary takes all the writes. When that's genuinely your ceiling, you split a big table into partitions or reach for an extension like Citus that spreads the data across many machines. But that's real work, and you do it once you're sure you need it, not before. And one more thing. Every connection to Postgres is its own operating system process with real memory behind it. A few hundred is fine, but a swarm of serverless functions, each opening its own connections, will bring the server to its knees. The fix is a connection pooler. PgBouncer is the common one. It sits in front and funnels thousands of clients onto a small, steady set of real connections. Put it in early, it saves a genuinely bad afternoon. So does everything go in Postgres now? No. If you need a pure, fast cache for a huge volume of simple reads, that's Redis's job. If your basic workload is spreading writes across many machines, a store built for that from day one will beat bending Postgres into it. And for heavy analytics over billions of rows, a column-oriented engine will be far faster. Postgres can do a lot, but can isn't always should once you're out at the extremes. Postgres uses a permissive license, close to BSD or MIT, and no single company owns it. It's run by a community that's deliberately set up so nobody can quietly change the terms on you. You've watched other popular open-source databases relicense almost overnight and send everyone scrambling for an exit. That can't happen here in the same way. So to sum it up,
you probably need fewer databases than you think. Postgres is one engine that does the work of your document store, your search, your vectors, your maps, and your queue. And it's honest about the costs, the cleanup, the single write primary, the connections. So you can start with Postgres and add a specialized tool when you know you for sure you need it, not before. You'll run less, debug less, and get page less. If that was useful, please like, share, and subscribe. Thanks for watching, and see you in the next one.